Welcome to the video key for quiz 7. Alright, so we're supposed to balance this reaction in acid, and one way to do this is to start by splitting it up into half cells. Okay, balance this reaction in acid. So we'll start by writing the two half cells. So we've got a nitrogen and we've got this aluminum half reaction. We're oxidizing aluminum to aluminum 3. And so now we've got to start by balancing. I'll just maybe write a middle column here where I'll put in what we're going to do. We're going to balance the oxygens with water. We're going to balance the hydrogens with H+, and we're going to balance the charge with electrons. Okay, so we'll do that separately, and then we have to find the least common denominator, put the reactions together, and we should be done. So first, balance oxygen with water. Well, we can see there's no oxygens on the right-hand reaction, so that's done. Balance the hydrogens. There's no hydrogens, so we're done. We do have to balance the charge, and we can see we're +3 here, and over here we're +0. So we need to somehow get rid of that. Since electrons are negative, if we add these to the negative side, we can see how that's going to give us the same charge, right? We're going to be +0 on both sides. And of course, if aluminum goes to aluminum +3, we've lost 3 electrons. That makes sense. So we're done with this side. Now let's do the other side. Well, we've got 3 oxygens on the left, but only 1 on the right. So we're going to add 2 waters to the right-hand side. And we have now 4 hydrogens and none on the left. So we better add 4 hydrogen ions over here. So we've done this, we've done this. What about the charge? Well, if we look at this, on the left-hand side, we've got, right now, it looks like we've got +3 on the left, and we've got 0 on the right. So we somehow have to make these numbers the same. If we add electrons to the left, we can make that neutral and we can make these the same. So we're going to add 3 electrons. So the net reaction we're going to get on the left is going to be 3 electrons plus 4H plus nitrate is going to go to mononitrogen monoxide plus 2 waters, and that should be balanced. As the hydrogen's balanced, oxygen's balanced, and the charge is now balanced. Okay, and then over here we have this reaction we've already done. So we need to put those reactions together. And to do so, we have to make sure that the electron transfer is the same for both reactions, right? So if aluminum is losing 3 electrons, it has to give the other side 3 electrons. And indeed, they're already the same. We don't even have to do at least common denominator. So now we just put these pieces together. And we do, the electrons are going to cancel. So we're left with 4 hydrogens plus nitrate plus aluminum goes to aluminum ion plus NO plus 2 waters. Now if we're done, everything should balance. So first, the aluminum balances, the nitrogen balances. There's 3 oxygens on the left and 3 oxygens on the right, 2 hydrogens on the right, 2 on the left. The charge on the overall reaction should balance too. So if we look at the charge, we've got on the left, we've got a net of +3. And on the right, we have a net of +3. So the reaction's balanced. So this is our final answer. Notice if we do oxidation numbers on our nitrogen atom, if you do the algorithm method on this, or you could do the bubble method if you draw out the structure of a nitrate ion, you'll see that the oxidation number for this nitrogen on this nitrate has to be, so oxygen, each one is -3, or is -2, and there's 3 of them, so that's -6. It nets out to -1. So this means each nitrogen is +5. And over here, we can see the nitrogen is just +2. So that means that what happens? It looks like we gained 3 electrons, right? Because if we add 3 negative electrons to +5, we're going to get +2. And indeed, that's what we had when we did the half cell method. So we didn't actually have to do the oxidation numbers, but that's like another check to make sure that we're right. Problem 2. We're going to make an electrochemical cell, and then we are going to do some stoichiometry with this. So first, let's do the cell. So this is a reaction that we might be familiar that if we look at the delta G standard for this, we see it's an unfavorable reaction. We're going to have to get it to run by adding electricity. So how can we tell that? Well, one way is to look at the voltage of the cell. So E is equal to E standard minus RT log RT over NF log of Q. But everything is at standard concentrations. That means Q, since all the concentrations are equal to 1, Q is going to be equal to 1. So if we take the log of 1, we get 0, which means that E is equal to E standard. So E standard, if we calculate that, we can see that that is just going to be the cathode minus the anode. So how could we form this from a cell? Well, if we look on our reaction sheet, we can see that we could break this reaction up into 2 pieces. We could imagine our hydrogen ion, or 2 hydrogen ions, being reduced to form hydrogen gas. Now we could oxidize the chloride ions to get chlorine gas plus 2 electrons. Okay, so we've taken electrons away from the chloride ions, so they go from -1 to 0, and we're giving those to the hydrogen ions, so they go from +1 to 0, and then 2 hydrogen atoms meet up to form H2. So notice if we put this together, we can see the net reaction is hydrochloric acid becoming the 2 different gases. So since this is reduction, the first reaction is reduction, this is going to be our cathode, and this is going to be our anode. And we can look up these reactions in our equation sheet to see what their potentials are. If we do so, we see hydrogen is going to be, our cathode reaction actually has a standard potential of 0, and our anode has a potential of 1.36 volts. So E standard is a negative 1.36 volts. And we already said that since Q is equal to 1, E and E standard are equal to the same number. So this is a negative potential. This is a reaction that won't happen by itself. We actually have to supply voltage. And the amount of voltage we have to supply is going to be equal to the amount that this is. So if we supplied a 1.36 volts battery, E would be equal to 0, and that would mean that the system would be at equilibrium. If we supply anything more than that, even a little bit more than that, we're going to be able to get this system to run. So we need at least 1.36 volts. And we want to get this up to a positive number to get this run, so we actually want a positive 1.36. But I just wanted to make sure you could calculate the voltage. So if you wrote negative 1.36, I'd mark that right. But 1.36 is the potential of this cell. But if we want to actually get it to run, we have to overcome that 1.36. So we would need to supply a positive 1.36 volts. Okay, so this cell, which would not be spontaneous, we can make it spontaneous by having an external voltage source. If we did, and 9 volts is plenty, if we use a 9-volt battery, how long would it take to make 3 moles of hydrogen gas? So we've got 3 moles of hydrogen gas. And any kind of electrochemistry, we want to get away from moles of chemical and go to moles of electrons. So we want moles of H2, and we want to convert that to moles of electrons. And we need to know that ratio. So we go back up to our half reaction, and this is what we see here. Here's our H2, and here's our electrons. So it took 2 electrons to make a mole of H2. So we should say that. 1 mole of H2, 2 moles of electrons. Okay, so moles of H2 cancels. We've got moles of electrons. We want to convert that to charge. The conversion factor is Faraday's constant. So we want to get rid of moles of electrons. We want coulombs of charge, right? C stands for coulomb, the SI unit of charge. And there are 96,485 coulombs in every 1 mole of electrons. So we've got charge. We want to somehow get that to time. So this is how much charge, we multiply this through, this is how much charge we need to supply, but we're supplying it at this rate. So 0.1 amps is the same way as saying 0.1 coulombs per second. So how much charge per second is flowing through the wire. So with that in mind, we can cancel these coulombs and get seconds, right? We said it's 0.1 coulombs for every 1 second. So coulombs cancel, and now we've got units of seconds. So this comes out to a pretty big number. This comes out to 5.8 times 10 to the 6th seconds. Okay, that's quite a big number. If you converted it, it's about 2 months if you convert it all the way up to days. So if you really wanted to do electrolysis, you need really big currents, not just milliamps. So if you try to do this with something like an iPhone charger, you're not going to get very far. Okay, that's actually numbered improperly, but anyway, the electrolysis problem. So here we're given, I'm going to shrink this down just a bit, we're given a electrolysis device and we need to annotate it. So we're given the reaction is the same one we just did. We're hydrolyzing or doing electrolysis on hydrochloric acid. So same reactions, and depending on which version of the quiz you have, the geometry is a little bit different, but in this case the right hand electrode is the anode. So we'll go ahead and label this as the anode. So we've got our cathode. And since we're reducing things at the cathode, we need to supply electrons. And electrons are going to flow, they never flow through the solution, they always flow through a wire. So we can show the electrons flowing up here. We can annotate that to show that we're flowing. And that means that we're generating them at the anode where things are being oxidized. So electrons are flowing down that way. And they're going to be pumped through the battery like that. Okay, so we've done our electron flow, and we could remind ourselves what the reaction is, the cathode. We said we were reducing hydrogen ion. And we were oxidizing chlorine, or chloride to chlorine. Okay, so we can see that the anode reaction generates electrons. Those electrons flow through the wire. Okay. Now let's see, what else do we have to do? We have to say the gas is collected in tubes. Which one's the chlorine gas? Well, we can see we're taking electrons off at the anode, and the thing we're taking electrons off of is chloride ions. So we have to supply chloride ions, or chloride ions are going to go like this, right? They're going to go wherever they are in the solution, they're going to flow into this tube. They're towards this wire, basically. And the hydrogen ions have to flow towards the other wire. And notice this means that we have a loop. If you follow negative charge in the form of electrons, it goes this way, clockwise through this wire loop, and then it returns by means of chloride ion through the solution. So electron, 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 chloride, but it's still a clockwise loop there. Okay. And since we're bringing chlorides over to this wire and they're giving up the electrons to the wire, these bubbles must be chlorine bubbles. And so the gas that collects over here is chlorine, the gas that collects over here is hydrogen. And unlike the electrolysis that we did in class, these are produced in 1-to-1 amounts. And since a mole of gas occupies the same volume regardless of what gas it is, the two tubes would be they'd be equal in size. So we have this going on. What else can we do? Let's check to make sure we finish the problem. We didn't label the cathode as positive or negative. So looking at our cathode, how does this work? Well, remember that in an electrolytic cell, we have a reaction that we're driving with our external voltage source. So if we want to reduce the hydrogens, which we did in the cathode, we have to pump electrons off the cathode. So we want to have a negative cathode. Okay, so electrons are going to be forced off the cathode onto the hydrogen. We want to make a positive anode because that's going to rip electrons off of our chlorine, or off of our chloride to make chlorine. So it's not easy to pull an electron off chloride, but if we have a positively charged anode, that's going to help us out. Electrons are attracted to it. Okay. So we've done that. We've labeled the flow of electrons. We've shown the cations and anions where they go, and we showed what gas was in which tube. Okay, so we're done with that one. All right, number 3. We have a weak acid. Calculate the concentration of fluoride ion in the resulting solution. We can make this a little bigger. Well, maybe not that big. Okay, so to do this, we can set up an iCheck table. And we'll remind ourselves we'll work in molarity here. So we have initial, we have change, and we have equilibrium. So we're given that we made a 1 molar solution. So you imagine taking 1.7 moles of HF and dissolving it in enough water to make a liter. So we have 1.7. And then as soon as you do that, some of it's going to react. But in that first microsecond or something before it dissociates, we could write it like this. And then some of it is going to dissociate, and we look at the stoichiometry, it's 1-to-1-to-1. So that means we'll lose x of this, but we'll gain x. Oops, I don't know why I have a 5 there. Gain x there. Okay. These are shown with pluses or minuses to show that this is a change, right? Well, if we add the initial and the change, we get the equilibrium state. So we've got 1.7 minus x, and x, and x. So we could write the equilibrium constant. It's concentration of hydrogen ion times concentration of fluoride ion over concentration of the intact undissociated acid. And these are equilibrium concentrations. So equilibrium in here, if it weren't equilibrium, this would be Q, right? But we want to use this number. So K equilibrium, we can rewrite this using this last row of our table. So we could say we've got x times x, and 1.7 minus x. You could just as well write it as C naught minus x, so you don't have to keep writing 1.7. Okay, so C naught just is equal to 1.7. Okay, so to do this, then we would have to solve for x, because x is the final concentration of fluoride ion. And if we assume that, okay, this is a weak acid, so that means that it's not going to go very far forward. So let's assume that x is small, that it's much, much less than 1.7. If that's true, then K equilibrium is going to approximately equal to x squared over C naught, right? Because this minus x isn't going to matter very much if x is very small compared to C naught. If we do that, then we can say x is approximately equal to, or I won't skip a step. X squared is approximately equal to K equilibrium times C naught. And now I can take the square root. And we can plug that in. So we have K equilibrium we said was 6.8 times 10 to the negative 4. And that was K, and C naught was 1.7. So if we take the square root of that, we get X is approximately equal to 0.034 molar. And if we wanted to, we could check our assumption that X is much smaller than 1.7 by plugging the answer we just got in right here. We could plug it in there and see if we get a different answer. So I'm going to go ahead and do that now. I'm going to plug that in and resolve for that X squared. So what I'm doing there is I'm taking this answer we have and I'm plugging it in the bottom here. So before we plugged in 0, we said it was so small it didn't matter. Now we're plugging it in to see if it really does matter, if it changes anything at all. So we had so we can plug that in. We can say X squared 1.7 minus 0.034. So 1.7, we subtract 0.034, and then we're going to take that number, multiply by K equilibrium, and take the square root. So K equilibrium we said was 6.8 10 to the negative 4. So we take that, square root, and our new X, we solve this, we get X is approximately equal to 0.034. It didn't change. So 2 sig figs, it didn't change at all. So, so we're happy with this number. So that concentration is okay for our fluoride. So we can say fluoride is equal to 0.034 molar. So notice the acid was dissolved at 1.7 molar concentration, but most of it stayed intact. Most of it is still in the form of HF, not in the form of the ions, because it's a weak acid. Okay, number 4. Calculate the value of delta G for this reaction. So we don't have delta H or delta S for these species on our reaction sheet, so the only route we have is to go through electrochemistry. So we know delta G standard is equal to negative NF E standard. So if we can find E standard, we can get delta G standard. So E standard is equal to E cathode minus E standard anode, and those we can look up. If we look at the copper, it is being reduced. So this is our cathode. If we look at the aluminum, it's being oxidized. That's our anode. So we look those up. So the copper reaction for copper 2 to be reduced is going to be 0.34. So we've got 0.34 volts minus, if we look at the aluminum being oxidized, so the reduction potential is negative 1.66 volts. And because it's an anode, we're actually oxidizing, not reducing. That's where this negative sign comes from in the equation. So this comes up to 2.0 volts. That's our E standard. And now we can find our delta G standard. So delta G standard is equal to negative N. So we have to say how many electrons are being transferred. So we can see the copper, each copper gained 2 electrons, but there's 3 coppers, that's 6 electrons. Each aluminum loses 3 electrons, but there's 2 aluminums, so that's 6 electrons. So either way you look at it, there's 6 electrons being transferred. So 6 electrons are being transferred from the aluminum to the copper. And then we plug in our Faraday's constant. And we plug in our voltage. And we can say 2 volts, but we can also remember that a volt is a joule per coulomb. That's going to help us cancel because these coulombs cancel, and so we end up with joules per mole, and that is what we wanted. So we end up with a pretty big number. We end up with a negative 1158,000 joules per mole. I rounded a little bit there. Or we could say that's negative 1158 kilojoules per mole. And that's it. That is the end of the video key for quiz 7. Thank you for watching.